Good afternoon. My name is Robert Voss, and I am the CEO of Sequoia Marine Solutions, or SMS for short. We are a brand new company based out of Fresno State University, located in Central California. As a new company, we have hit the ground running, growing to an organizational size of over 50 employees. What you see today in front of you is the culmination of over 5,000 hours of our employees' passion and dedication. Today, I'm proud to present to you Rosie, our remotely operated submersible for innovation and exploration, and Adam, our aquatic drifter for autonomous monitoring. We will showcase to you their features, as well as guide you through the development cycle that got us here. This cycle began by us implementing a culture of safety within our company, which is why safety guidelines and standard operating procedures were implemented at the very beginning of SMS's establishment. Santiago, our Chief Safety Officer and man of many hats, will further expand upon this culture of safety.
Safety is our highest priority. To maintain a safe working environment, all engineers working on the ROV must pass our lab and power tool safety certification required by our university. I apologize. Alongside being OSHA 10 certified myself, a CPR and first aid trained individual is also present during practice. During practice, we use both a checkoff list and a job safety environmental analysis document, which helps us mitigate any potential hazards that may occur during, before, and after deployment. Some safety features that we have incorporated is our thruster shocks and a fuse, which protects our engineers from any possible lacerations or worse, electrocution. Most importantly, we empower our engineers with a stop work authority, which allows them to stop all operations if they identify any unsafe condition. Now, safety empowers us to learn both technical and leadership lessons, which our Chief Technical Officer, Declan, will discuss next.
Our company started with two members, Robert and I. Transferring into Fresno State, we want to use our prior maintenance experience to bring the same opportunities we were fortunate to have to our university. Starting out, we recruited members, many of whom had no prior experience with me. Given our low barrier to entry, we learned that some members lack experience, which we built up by holding over half a dozen workshops and a project competition prior to the season. On the technical side, we learned that testing was effective for bringing theory into practice through the initial over-engineering of our manipulator. As a team, we learned to be flexible and adaptive as we had members, including some team leads, drop out over the season. Even then, we learned that standards and procedures are absolutely key within a large team to maintain that efficiency. This process has been incredible for ourselves as engineers and individuals, which allows us to apply this year's theme and tasks, which Anna Paula, our RV chassis propulsion team member, will discuss next.
As ocean monitoring efforts continue to expand, researchers are increasingly relying on vertical profiling codes to collect critical ocean data. And although some programs like GeoVGC have demonstrated their value, operating beneath ice creates unique challenges that require reliable under-ice monitoring. Adam right here was developed specifically for this. By changing its buoyancy, the float is able to collect data throughout the water column while also addressing some of the same challenges faced by profiling floats. And while Adam focuses on environmental data, Rosie right here performs the hands-on work. And to maximize task completion, Sam led the design of a multi-purpose tooling suite, which, when paired with the 6-degree of freedom propulsion system, enables the installation, recovery, and servicing of subsea observatories, eDNA sensors, and lobster ponds. Now, to discuss more of the design philosophy, I'll hand it over to our Chief Design Officer, Caleb.
Rosie and Adam's most marketable feature is the serviceability we baked into their manufacture and assembly. SMS takes pride in designing as many parts in-house as we can, and we do this using checklists to ensure that every part is easy to make and assemble. This directly applies to the 68 unique 3D printed components of Rosie's chassis, her custom machined and anodized backplate, and the 20 plus parts inside of Adam. It's these sheet metal parts that enable a quick adjust ballast system that let us increase or decrease buoyancy in 1 or 2% increments simply by adding or removing stainless steel plates. This stainless steel sheet metal system also enables a quick removal top flange that allows us to remove all internal electronics and our buoyancy system at once, simply by taking this part out, allowing us to go from servicing electronics on the surface to in the water and profiling in under 1 minute. This is a system design of serviceability, and that's what drives our chassis, which Dottie, our chassis lead, will discuss next.
We had three main goals when it came to the design for Rosie's chassis. First and foremost was safety, which Santiago talked about. Next was versatility and modularity. To be as versatile as possible, we needed 6 degrees of freedom to move around in the water. So to achieve this, my team member Carlos developed these 4 thruster mounts that you see on the corners of Rosie. These spread our T200 thrusters apart to avoid thruster wash, which is when they feed into each other and leave you down the water. And with 4 pointed vertically and 4 at 45-degree angles, we can now move however we need to perform any task. Now, with modularity in mind, we lined our chassis with aluminum T-slot rail. This was a dramatic improvement from the PVC pipe that we originally lined our chassis with because it reduced the chassis mass by 60% and we could mount anything we wanted onto it, from our thruster mounts to our manipulator, which our manipulator team lead Sam will talk about next.
So Rosie is equipped with 2 manipulators. The rigid harpoons mounted to her feet were originally designed to only collect the basket stars, but now our pilot Memo now uses them to complete up to 4 mission tasks in a single trip. As Declan mentioned, the manipulator prioritized rapid testing. We built 3 distinct prototypes and selected a lead screw powered design and parallel motion at the gripping point because that design could complete 100% of the manipulator mission tasks. In addition, that design includes TPU grips and a wrist rotation that is capable of 360-degree wrist rotation. So the TPU grips, designed by team member Ethan, went through 11 iterations before selecting a fin ray grip design that can bend around any object, specifically for the the coral substrate is very effective for that. And the rotation frees up our pilots as they can rotate the end effector without having to roll the entire chassis. And to elaborate on that design, my team member Giovanni will elaborate.
The wrist rotation enables our pilots a greater ability to pick up and reorient objects. Specific tasks such as removing the biofouling will require us to grab onto and rotate a handle. The rotation is achieved via 2 gears and a motor. There's going to be 1 unpowered gear attached to the back plate of the claw, and it's turned by this power gear, which is attached to our 16-to-1 gearbox, which is powered by our rotation motor. The gearbox was 3D printed in-house because it's cheaper and it's easier to manufacture than metal gearboxes, and it isn't prone to corrosion like metal gearboxes are. The reason we went with the 16-to-1 ratio is because the 16-to-1, Caleb did some torque calculations that showed this ratio would allow us to rotate the heaviest objects in the pool. And we wouldn't be able to rotate anything if we couldn't control the manipulator, which ROV Controls and Electronics lead Ansh will be discussing next.
Rosie utilizes 2 48-volt to 12-volt buck converters. Through testing, we found that 1 buck converter wouldn't allow us to use the maximum amperage we needed to power our thrusters and motors. Declan found that using 2 buck converters can let us reach the 30 amp maximum we were allowed to use. To centralize power, we use a power distribution block, and for vision, we use 2 car automotive backup cameras because they're cheap and waterproof, alongside a blue robotics camera for a high resolution feed for the craft scan and photogrammetry tasks. To power our thrusters, we use 10 ESCs that contain a 12 to 5 volt step down that powers our onboard computer and sensors. For small corrections in water, we use an auto leveling system that corrects our yaw, pitch, and roll using an orientation and depth sensor. To talk more about controlling the ROV itself, I'll be passing on to our ROV Controls and Electronics member, Memo.
At the server side, we have a 48-volt power supply. We also have our 2 Flight 6, 1 Xbox controller, and 2 laptops. When we're actually sending inputs to the ROV, we're using 2 really popular libraries. We're using XInput and Direct Input and sending that data via networking packets. We chose to use these libraries because they're really popular, so there's a lot of documentation for us to learn and troubleshoot with. When my teammate Chloe and I were first implementing the motion control system, we noticed our implementation was a little too specific to our model. So if anything were to change, specific thrusters, etc., we would have to do things from scratch. So with the help of our programming lead Dalton, we refactored a whole entire code base using dependency injection and clean architecture-based ideologies to achieve industry-grade modularity by abstracting out a lot of those specifics. But an ROV isn't complete without a float to monitor the environment, so I'll be handing things off to our float chassis lead, Cal.
Our main goal for the float was to create something that would not only complete this year's competition task, but be adaptable to next year's competition task. So, with that in mind, all of our parts were purchased and tested specifically for the cold this year, especially our peristaltic pump right here in the center. We tested it with ice water first, and then with a simulated EGAD solution, and then finally we tested it in the freezer to make sure that it would be able to handle the cold start at the bottom of the pump. My teammates Caleb, Liz, and Kellen ran the calculations, and we determined that the discrepancies we found were suitable for the pool competition requirements, so we decided to move forward with our peristaltic pump as our primary buoyancy engine. Also, for organization, as Caleb mentioned, we have designed in-house our sheet metal rails that come out through the top flange. We have a vertical shelf and a horizontal shelf, interchangeable to keep things organized, electronics at the top, water contact, and components at the bottom. Now I'll be introducing Wyatt, who is going to speak on our flow control electronics.
For the float electronics, we primarily focused on three main elements: simplicity, reliability, and an effective control system. For simplicity, we use a Raspberry Pi Pico programmed in Thaughty and MicroPython, since that was the easiest toolchain for us to utilize. For reliability, we made a custom designed PCB to house all the electronics. The electronics that aren't on the PCB are ones that are dependent on position based on position, such as the depth sensor, the motor, and the power. For our control system, we simulated it in MATLAB and Simulink first, so we could quickly tune the PID loop that we use to control it, so that when we do actual water testing, we could tune quicker and more effectively. All this, however, requires a fair bit of funding, so I'll head over to our Director of Finance, Jaime, to talk about how we get our money.
At Sequoia Marine Solutions, one of the largest challenges that we faced as a first-year team competing at Fresno State was that we simply didn't have any previous budget projections or any estimates to go off of. So a lot of our budgeting and planning was mostly based off of previous robotics experience among our employees, as well as deep vendor research to ensure that we 3D printed as much as possible, not only bought what was necessary, as well as getting the best bang for our buck for every component. This lean construction principle that we used to build the ROV was also good on the business side. We developed a custom CRM template to track over 200 potential sponsors and grant opportunities, ensuring no stone was left unturned in our financial journey. On our financial journey, we also built a pop-up food stand where we generated over $2,000 in profit in just 3 days. Additionally, with support from Mesa and Fresno State, we were able to create K-12 workshops, teaching students the importance of getting involved with STEM, science, and most importantly, ocean engineering. We'd like to take the time now to thank our financial sponsors. Thank you to Precision Civil Engineering, IEEE, Macmillan Electric, the Schmidt Ocean Coalition, the Maine ROV Organization, the Marine Technology Society, and many others who have supported us on our journey. We'd also like to thank our in-kind donors, such as Colin Warrens, BW Packaging, Juan Robledo, our mentors, Dr. Millam and Dr. Wu, as well as another mentor, Adam Garabedian, and many others who have helped us along the way. Thank you to the Berg family for housing us at every water testing and feeding us every time we were there. Now, who better to end it off than Robert, our CEO?
Our company was guided by three primary principles: versatility, maintainability, and modularity. These can be seen across our entire organization. Whether it be our custom code base that was specifically designed with part swapping in mind, a modular chassis that allows the complete disassembly and reassembly of Rosie in under 2 hours, or a leadership structure that was designed for versatility in the face of our busy college schedules. Our goal is not just to win competitions and build cool robots, but that's kind of cool too. But our goal is to create opportunities not just for ourselves, but for the next generation that not only further our ambitions, but help us utilize the skills we have gained to provide a positive impact to the world. Thank you all very much for your time today, and we would be happy to answer any questions that you may have.
So, you started the presentation off with safety, and you did touch on it from time to time. I'm always interested in lessons learned from safety. Can someone tell me about some type of safety incident that really helped you make things safer throughout your journey?
I think one thing is all of these parts are 3D printed, like the vast majority. I mean, anything we could 3D print, we printed. And these, especially these ones, require a lot of supports. And it's just kind of a common thing, like, there's supports and you have to tear them off. But it turns out there's some parts that end up being sharp. And so using gloves, it seems like, oh, they're just supports. You should just take them off. You shouldn't have to need gloves. They're made to come off. But turns out they can scratch you. And so I've learned that throughout the process. I've printed a lot of ended up printing a lot of these mounts, and it's important to, I've started wearing gloves after so it's been very helpful for me.
Yeah, another one of our safety things, so the electronics at the top, I had my teammates Chris and John design for having electronics at the top, all the water contact components at the bottom, because at one point we forgot to put a stop function into our code, and so it just kept infilling with water, and the bladder just started to fill up, and it was like, oh, why can't we see inside the like it's filling up with water, and so we had a teammate go in to save it, and when he saved it and pulled it out, the water was literally almost right up to the electronics, but
It was so urgent he had to do it without a swimsuit. So every time now we have stop conditions in our code to make sure that doesn't happen again.
Thank you to Matthias for saving.
Yeah.
There's no sacrifice.
It's a great way to learn. We're in the caps, so is there why does some have caps on?
Those of us with caps on are the pilots and co-pilots. So Mel and I are the pilot and co-pilot of the ROV, and then Cal and Wyatt are the pilot and co-pilot of the float.
So we go back to the water for a second. You have the water in the same chamber with the electronics, and it just doesn't reach it. Is that
For the
what you
float?
said, or
The idea is that
loosen?
the idea is that if the bladder fails,
Okay.
the water, because it's on the bottom,
Yeah.
it'll
Forces it to
basically we have time because as it fills up, it'll fill up from the bottom.
Yeah.
So we keep the electronics separate in a sense.
Okay.
Right? If we kept the electronics close to the ballast, then or to the bladder, as soon as it fails, then those electronics will get cut. So we have time to pull it out.
Okay.
which is-
But the only thing that's separating the bladder and the
yeah, we don't have a layer system that's still yet, but we did that as kind of a compromise to.
The main point is that the water is not supposed to escape the bladder, period. And
Right.
Yeah.
But in the event that it does, we want to keep our electronics safe and not discharge any voltage in the water.
And how much testing did you do with the actual props to ensure that you're convinced that you're going to be able to execute the missions? And did you do any work in like optimizing tools and changes and anything you have to do to talk about that?
To start, we were in the water for 33 days this season. 18 of those were post-qualification with a fully functional ROV. That was really just an optimization season. I'd love to pass it over to Sam if you're willing, just to talk about all the optimization we did to our manipulator. We started the season with a manipulator that was failing to pick up anything at all. And we were able to, post-testing those three, get it to where it can pick up literally every object it needs to in the pool. So Sam, if it's okay, I'll pass it over to you.
Yeah, so when looking at the testing this manipulator, before it had the actual rotation, so most of the grip strength, it's powered by a lead screw, whereas a connector under here, it's guarded right now. But there's a lot of play. So if you can move this when it's not on, or when it's just the amount that you can move these separate, that really makes it kind of was the test, the biggest, easiest way to show that it has strength or not. And so getting rid of any play. So there's lots of linkages in this design because it distributes the force well. However, that means that all of these parts are 3D printed. And this is my first semester ever 3D printing anything. And so figuring out, okay, how do we tolerance this? How do we deal with the amount that parts shrink? And so between the links and figuring the tolerances, that was one of the parts that would reduce the play. I think the biggest thing that changed that reduced the play though was using heat set inserts. So heat set inserts, you heat up the metal, it's a metal thread, and then you put it into the hole, and then the PETG filament cools around it. And so they're all 3D printed, so using the lead screw, it was originally just grinding against the 3D part. And so putting a heat set insert really reduced that wear, and we put that on both the connector part that moves back and forth linearly and the mount of that lead screw. And that really reduced a lot of that play.
To add on to the optimizations that we made, as mentioned in the presentation, we have a fully custom code base. So all of our software is pretty much custom to us. And we wanted it to be as modular as possible. So some of the things are in kind of different pieces, and so they have to be started separately. So at the beginning, we would have to go in and kind of start everything, bit by bit. Start the ROV side, start the surface side, and start the controllers and start the cameras. Now, one of the optimizations that Launch was able to make was to write a couple of different scripts that can start in different sections. So if we only want, the cameras and not the ROV side, we can do that. Or if we just want everything, instead of it being like 5 clicks, it's all 1 click, which drastically improved our practice time, as well as just the time to, okay, we're plugging things in, to, okay, we're in the water and we're off performing mission tasks.
Additionally, one more thing to add to that question, in regards to optimization and the mission tasks, I'd like to give a lot of credit to our pilots, Memo and Dottie as well, for strategizing what order to do the missions in. I'm unsure, maybe that's also what you want to address with the question. I'd like to give a lot of credit to them as well. They can kind of discuss, they decided to order with what task they were going to complete first, most optimal path. So if you guys want to talk about that a little bit as well.
Yeah, I wish I had the little checklist that we have, but it's like one checklist that we don't have on the table. But basically what we did is we analyzed the tasks and discovered the best route for our machine. We can do multiple tasks at once because we have a rotating manipulator and these harpoons. These harpoons come in really clutch. So we can pick up 2 basket stars and a coral all at the same time. We can also do the eDNA and rotating the, what is it called? The biofouling exactly at the same time. So just being able to figure out what we do at the same time, what is going to take longer, like photogrammetry would take about 8 minutes to fully render. So doing that earlier in the run rather than later, and just things like that.
If you guys had a chance to change anything about this, what would you change?
One of the big things that this year we weren't necessarily able to get around to due to time and experience constraints is actually creating a custom motherboard setup for the internals of the chassis. This is a setup that I'm very familiar with because we have used it previously, and we really wanted to create a setup where everything is drop-in, close shut, and that's it. We didn't want to use any wires or anything, and so with that, not only would this motherboard setup allow us a lot easier time servicing parts because it's just you disconnect 2 contact patches, you take an ESC out, and you replace it. There's no wires to mess with or anything. That would help with our maintenance time as well as the ease of maintenance, as wires are a bit more difficult to get around than if you've already structurally laid out where you want the person who's servicing the vehicle to have the easiest access. So going forward, that's something that we definitely want to implement, and it's something that we thought about doing this semester, but figured we'll run with what we have, we'll make it work, and then in the future, we will note it down as an improvement.
Another thing, it's fairly simple, but having an external power switch to the float, we never had the time to machine and figure out which one of those we would use. We saw many teams here use them, and they're really convenient because we basically have to power our electronics and then seal it. And for a while, we used timeouts before we had our wireless communication nailed down to handle that. So, and that was fairly annoying for the early stages of troubleshooting. It's part of the reason why we moved to simulation of our control system as early as we did, because it took a long time to manually tune our control system. So that's just one of the things I would change, is just having a simple external power switch to the float.
Two quick questions. One, about the cameras. So why did you choose to go with that configuration of the 2 backup cameras and the one from?
So from earlier years, Declan used to be on a previous team, Crushed That, and from there he heard from a team from Hong Kong that car backup cameras were IP69K waterproof rated, which is rated for a 5-meter depth, like waterproof tested for 5-meter depth. And so the price comparison between these 2 cameras is, this is 50 USD, while this is 360 USD. And it provides relatively the same quality, but for actual programming tasks, this has a higher pixel rate compared to the automotive backup camera. So this is mostly used for vision for the pilots, and this is for the actual scanning of different tasks.
Okay, second question. What did you sell at the food stand to make $2,000?
So we were able to pull in $2,000 of profit. The way that we did it, we just kind of asked our members, hey, you guys like boba? You guys like fried chicken? Like French fries? Well, maybe you don't, but we're gonna go ahead and sell that. But it was a mildly democratic process. It was just some food that we all figured would sell well at a festival area. There's an event at our school called Vintage Days that's hosted every year. So you get 3 days. You can apply for a food booth, pay a fee. You get to put your stand up. And so yeah, that's what we sold. It was a very interesting combo, but it was honestly a very stressful but very fun time operating it.
I'm sure it was team building.
I think I gained a few pounds that weekend.
It's all thanks to Santi's cooking.
Yeah.
Why do you guys have 2 joysticks, like, and then the Xbox controller?
You got that?
Well, one, they're really cool. Originally, we had 2 Xbox controllers, but we were kind of worried that they weren't going to have enough buttons for us. We have a lot of shortcuts on these, but also a lot of manual. So I believe this is left stick. You twist this to go up and down, or if we don't want to do that, we can also use this. But it was mostly for buttons. We were worried that we were going to run out of buttons for things that we wanted to do. This controller is used for manipulator, but just in the event that we needed, something happened, we also have a little bit of manipulator control on this controller, which we wouldn't be able to do on another Xbox controller, just again, due to limitations of the amount of buttons.
In addition, there's the precision of the joysticks. Like using a small joystick with your thumb, right? You don't get as much finesse, the specificity, where when you have 2 different ones in each hand, you have really full control over which direction
Yeah, more
you're
of a
going.
range of motion.
Yeah. And another feature of these controllers is that these little sliders at the bottom also control how fast you can go in the water. So one is for how fast these outer thrusters move for spinning, and the other one is for vertical and horizontal movement.
And finally, on that note, one of the nice things about these controllers having so many buttons, like was previously mentioned, is that we were able to make a complete and customizable debug mode on the fly with these buttons. Various buttons on here allow us to go into different kinds of debug modes to test a variety of situations that we might run into in the field. And so not only did we have more linear and granular control with all ranges of motion with these controllers, but also if anything were to happen in the field, we'd be able to figure out what's wrong and service it as soon as possible.
Yeah. Excellent presentation.
Thank you.
Thank you.